So here we have a example that is related to dimensional analysis, and this example is from your Munson book in chapter 7. This is the first example of chapter 7, and let's read out the statement. A thin rectangular plate having a width and height h is located so that it is normal to a moving stream of fluid as shown in figure 7.1. So this is the plate, and this plate is normal to this flow stream. Assume the drag D, the drag force that the fluid exerts on the plate is a function of W, that is the width, and H, that is the height. It is also the function of fluid viscosity, density, respectively, and the velocity of fluid approaching the plate. So from the statement we can say that the drag force is dependent on the width of the plate, the height of the plate, and as you can see, these variables are mentioned on the diagram: the width, the height, the velocity, density, and viscosity. So the drag force is dependent on these variables. So what we are required to do is to repeat the same 8 steps that we previously studied and determine our suitable pi terms. So this is our dimensional analysis problem, and here a plate is being placed through which a fluid passes, across which the fluid passes, and the fluid is exerting a certain amount of drag force on this plate, and we are required to find the suitable pi terms. So let's move on and solve this step by step. So the first step is to list all the variables that are involved in the problem. So the variables that are involved in the problem include the dependent variable and the independent variable, and as we can see from the statement, our dependent variable is the drag force, and this drag force is dependent on the width of the plate, the height of the plate, and the density, viscosity, and velocity of the fluid. So we can say from the statement that these are our variables. The drag force here, right, is the dependent variable, and the width, height of the plate, that is related to the geometry. These two variables are related to the geometry of the plate, and the density, the viscosity, density, and velocity, these are related to our fluid that is flowing past this plate. So we have 6 variables. One is dependent variable, and the other 5 are the independent variable. So this was the first step when we start our dimensional analysis. The first step is to list all the variables that are involved in the problem, and in this problem we are studying a drag force, and the drag force is influenced by these parameters, these variables. So this was our first step where we identified our key variables, and in total we have 6 variables. So step 2 is to express each variables in terms of their basic dimensions, and as you remember, we defined basic dimensions as our we can have 2 systems of basic dimension. One can be the mass, length, time system, and instead of mass we can also write force, length, time. So what we are required to do now is to write the basic dimensions of all these variables that we just defined, and let's do that. So here drag here is a force. Drag is a force, so it will have the basic dimensions of a force, that is a mass, that is kilogram meter per second square. So that's why it is mLE minus 2 to the power. Width is a length, so it will have basic dimensions of a length. Height is also a length, so it will also have a basic dimensions of a length. These are the basic dimensions of our viscosity, the dynamic viscosity. These are the basic dimensions of our density, and the basic dimensions of our velocity. So this was our step 2, in which we have to identify these variables with respect to their basic dimensions, and we have to follow one system, and that system was our MLT system of our basic dimensions. So in the previous slides, when we were studying dimension analysis and we were studying the pressure drop per unit length, we were following the FLT system. But as you remember, in the end, we saw that the pi terms that we just derived in the previous slide, we also wrote them in terms of MLT system to see that they are dimensionless. And at the end, in this example, we will also represent these terms in FLT terms, and we will see that are they dimensionless or not. So if you start with any of these system in the start, if you start with MLT system or the FLT system, in the end you will have to convert in between them to see that your pi terms are actually dimensionless. So no matter what system you select at the start, you will have to convert them to the other in the end to see that your pi terms are actually dimensionless, and this is what we are going to do at the end. In this example, we are following the MLT system. As you can see that are our variables, their dimensions comprise of all these three, or one of these three, or two of these three basic dimensions. So these are our basic dimensions of our variables involved in this example. So now let's move on to our step 3. Now let's move on to step 3, and in step 3 what we need to do, we need to determine our pi terms, and to determine our pi terms we need to use the Buckingham Pi Theorem, and the Buckingham Pi Theorem tells us that the number of pi terms will be equal to k minus r. So k is the number of variables that are involved in a particular experiment, and r is the number of dimensions, the minimum number of dimensions that are required to represent these variables. So as you already know that our number of variables are 6. We have 6 variables as we previously defined in the previous slide, and these 6 variables are my drag force, which is the dependent variable. The if we can just look at the list, these are my 6 variables: the drag force, the width of the plate, the height of the plate, and then the viscosity, the density and velocity of the fluid. So here k is equal to 6. K is equal to 6. So these are my 6 variables. Both I will have to count both the dependent and independent variables in this term. So k is equal to 6. These are my number of variables, and the minimum number of reference dimensions that are required are 3. R is equal to 3, because you can see that the minimum number of reference dimensions that are required to represent all these 6 variables are 3, that is M, L and T, the minimum number of reference dimensions that are required to represent these 6 variables. So by using Buckingham Pi Theorem, k minus r, that is 6 minus 3, what I will be left with is 3. So in this particular example, I will need 3 pi terms. For this particular example to see the effect of drag force due to these different variables, that what will these different variables affect the drag force, and for that purpose I need 3 pi terms. And if you remember why we use the Buckingham Pi Theorem and what is the purpose of the dimensional analysis, just to repeat that dimensional analysis is done to reduce the number of experiments and actually form our dimensionless terms that will be used to see the effect of the variables on a particular dependent variable. So in this case, our dependent variable is the drag force that will be subjected on the plate, and the independent variables are width, height, the viscosity, density and velocity. So we will see the effect of these variables on this variable. So this is what the whole point of the dimensional analysis is. We need to reduce our number of experiments, because changing all these dimensions, the variables one by one, and seeing the effect of drag force by changing these variables, it will be a very large number of experiments and they will be very expensive for us. So we need to have pi terms to easily see the effect of these variables, these 5 independent variables, on the dependent variable, in this case the drag force. So this was our step 3 in our dimensional analysis, to determine the number of pi terms that are required, and for that purpose we used our Buckingham Pi Theorem that is used to determine the number of pi terms. So in step 4 we are going to select our repeating variables, and as you remember, repeating variables are those variables that are going to be repeated in these three pi terms. So let's say that now we have three pi terms. We have three pi terms, pi 1, pi 2 and pi 3. So we need to select three variables from the list of the 5 independent variables that we have, and we will select them so that they will appear in all these three pi terms. The repeating variables will appear in pi 1, in pi 2 and in pi 3. That's why they are called repeating variables, that they appear in the pi terms again and again, depending on the number of pi terms that we have. So they will appear in each of the pi terms, and we will select them from the independent variables, because the dependent variable cannot be taken as the repeating variable. So we will have to select them from the independent variables that we have, and in this case the independent variables are width, height, viscosity, density and velocity. So the condition for selecting repeating variable is that they should be dimensionally independent. And by dimensional independency, let's define that. What does dimensional independency mean? Actually, here in this example, they are selecting these three variables, the width, velocity and density, as three repeating variables. And a quick inspection of these three reveals that they are dimensionally independent, since each one contains a basic dimension not included in the other. Note that it would be incorrect to use both W, that is the width, and height as repeating variables, since they have the same dimension. So let's say, what does this mean? Here we have selected our width, velocity and density as our repeating variable, and they are saying that they should be dimensionally independent, that these three repeating variables must be dimensionally independent. What does dimensional independency means? First of all, we will write their dimensions. That is the length, per time, and that is mass per unit volume, so that is mass per cube. So this is how we can represent these three dimensions. So for dimensional independency, each of these variables must have dimensions, and these dimensions must contain one term that is not repeated in the other. As you see that in case of velocity, we have time. So you can see that time is not repeated in the width dimension that we have, which is equal to the length, and nor is it repeated in the density, that is mass per unit length. If you see the density, here we have mass, and mass is not repeated in the velocity and again in the width dimension. So this is dimensional independency, that each of these repeating variable must contain a dimension that is not repeated in the other. And as stated in this statement, we cannot take width and height both as our repeating variable, because by taking height as our repeating variable, then we will have two dimensions, that is, we will have two variables with the same dimensions. We will have two variables with the same dimensions, so this will not be dimensionally independent. These repeating variables will not be then dimensionally independent. So we will have to select those variables that are dimensionally independent, and dimensional independency means that they must have one dimension at least which is not repeated in the others. So this is what dimensional independency means. So let's now move on to our step 5, and as now we have selected our repeating variables, and the next also the number of repeating variables must be equal to our number of reference dimension, and as we already saw that the number of reference dimension R is equal to 3. So we have 3 reference dimensions, so that this will be the number of repeating variables. We need to select 3 number of repeating variables, because the number of our reference dimension is equal to 3. So this was our step 4, which was very important, because in this step 4 we will need to analyze the dimensions of each of the variables and need to select those that are dimensionally independent. and as you already know, dimensional independency means that each of these variables must have a dimension that is not included in the other that we just saw. So now let's move on to our step 5. So now let's move on to step 5. And in step 5, what we are going to do, we are going to take one non-repeating variable and multiply them with our repeating variables that we just defined in the previous step. So let's see that our repeating variables were the width, the density, and velocity. So we will take these repeating variables and multiply them with one non-repeating variable. So the drag force is my non-repeating variables. I'm encircling them. The height is my non-repeating variable, and the viscosity are my non-repeating variables. So I will take this drag force first and will multiply them with the repeating variables to form my first pi term. And this is how I'm going to do that. This will be my pi 1 term. So pi 1 will be equal to my non-repeating variable, in this case the drag force, and it is multiplied with the repeating variables, in this case the width of the plate, the velocity of the plate, and the density of the plate. I will also raise the powers of the repeating variables to certain alphabets, in this case A, B, C, and then I'm going to write their dimensions. I will write their dimensions, the dimensions of these variables, and then I'm going to equate them to my 3 reference dimensions, and they will be in this form, they will be dimensionless. So now let's write their dimensions. Now let's write the dimensions of these terms and equate them to a dimensionless entity, in this case our 3 reference dimensions, the MLT, and they are dimensionless. So this is how we are going to write it. These are my dimensions for force, that is my non-repeating variable, and then my repeating variable width, and then my repeating variable velocity, and my repeating variable density. So in terms of dimensions, I am representing the pi terms and I am equating them to my 3 reference dimensions, and I have raised their power to 0, so that right hand side must be equal to a term that is dimensionless. And this is where the dimensional homogeneity also comes into play. Now I will have to determine the value of A, B, C, so that I can arrange these terms in this pi 1 term, these repeating variables, such that they are equal, they are also dimensionless. So what I'm here is doing is I'm applying the principle of dimensional homogeneity, and principle of dimensional homogeneity means that my left hand side will be equal to my right hand side. So the term on my left hand side must also be dimensionless. So for that purpose I am doing this step to actually arrange these terms in this pi 1 in correct order, so they also appear dimensionless. In this case, then my left hand side will be equal to my right hand side. So now let's correctly assume the values of my powers A, B, C, and then we will correctly arrange this pi 1 term. So thus for pi 1 to be dimensionless, it must follow that 1 plus C is equal to 0 for our dimension of mass. Why this is 1 plus C? Because here you can see that the mass dimensions appear in the force term right here, and it has a power of 1. So this is why 1 is written here, plus C. And then the mass dimensions appear in this density term, and here it has a power of C. So that's why 1 plus C is equal to 0 for mass. Now let's see for length. For length it is 1 plus A plus B minus 3C. So for length, if you can see that in the first force term, the length power is 1. So that's why it is 1. Then here in the width dimension, the length have power of A. So that's why it's plus A. We are actually adding the powers of each of these reference dimensions. So then in the velocity term, the length has a power of B. So that's why it's plus B. And then in the density term, the length power will be, it is minus 3 multiplied by this c, so that is minus 3c, which is equal to 0 for length. And on the right hand side you can see that it is its power is 0. Similarly for mass, on the right hand side the power of mass is 0, so that why they are also equated to 0. Now for time, you can now relate to these equations, that how are we writing them. In the first, the force term, we have time to the power minus 2, and then in the velocity term we have time power minus 1 and multiply by this b, so that's why it's minus 2 minus b is equal to 0, that is on the right hand side. So this is for time. Now I am going to write the values of a, b, c, and then I am going to write them in this pi term and correctly write my pi 1 term, and by doing this I will have my first pi term. So these are my values, and these are my values of a is minus 2, b is also minus 2, and c is minus 1. So the pi term then becomes like this. This is how my pi 1 term will become by putting in the powers a, b, c. So this is how it will become, that the drag force will be in the numerator, and these width, velocity and density will be in the numerator denominator. And now you can see that we have also written the powers of a, b, c in their correct terms that we just found. So now a was 2, a was minus 2, so now it moves to the denominator, so it becomes 2, so it is w square. And then for velocity, b is minus 2, so that's also in the denominator, and c is minus 1, so that will also move to the denominator. So this is my first pi 1 term that I wrote, and now I have to repeat the same procedure for determining my two other pi terms. Those are my pi 2 term and my pi 3 terms, because we already defined that we have 3 pi terms. So now let's move on and repeat this procedure for pi 2 and pi 3. So step 6 is to repeat step 5 for each of the remaining non-repeating variables. And again, if you look, just examine that these are my repeating variables, and I have formed one pi term by using this non-repeating variables. Now the other non-repeating variables that remain are my height and viscosity. So now I will take my height and multiply them with the repeating variable and form my pi term, then raise them to the power a, b, c, equate them to a dimensionless reference dimension MLT, and equate my powers a, b, c, and write the correct order of my pi 2 term. So let's do that. The next procedure is repeated with the second non-repeating variable, that is h, that is the height of the plate. So height of the plate is my second non-repeating variable. Now let's form pi 2 term, that is my non-repeating variable multiplied by my repeating variable, and again those are my width, velocity and density in this case, and they are also raised to the power a, b, c. So now I'm going to write their dimensions and equate them to 3 reference dimensions that I have, and raise their power to 0, because I want my left hand side equal to the right hand side, and again my right hand side is dimensionless, so I want my left hand side to be dimensionless. So my left hand side to be dimensionless, I need to equate my ABCs to correctly arrange my pi term, so that my whole pi 2 term also is dimensionless. So this is how we are going to do. First, for mass m dimension, for m has a power of c, so m mass is not repeated in any of these variables. As you can see, the dimension of height is L, the dimension of width is length, and dimensions of velocity is length per unit time. So the mass term is only included in the density, that is mass per unit volume, and it has a power of c. So c will come on the left hand side, and on the right hand side mass has a power of 0, so c will be equal to 0. Then again we'll repeat the same procedure for length L. And so length here has a power of 1, then it has a power of a plus a, then it has a power of b, so plus b, and then it has a power of minus 3 multiplied by c, so it has this term minus 3c and equated to this 0. So this is for length L. Then b, for b, for time t, we will take b, the power of b, and equate that to 0. So the time is only repeated in the velocity dimension. So time here is has a power of minus 1, multiply this b, so it will come b is equal to 0 into this. So now we have, from this three equation, we can easily find our ABC terms, and my ABC in this case are a is minus 1, b is 0, and c is 0. So now I am going to write these here, write these ABC here, and correctly arrange my pi 2 term. So by writing the ABCs, I will get pi 2, that is h over w, because my a is minus 1, a is minus 1, and b is 0. So anything raised to the power 0 is 1. So c is also 0, so it will also be 1. So my velocity and density will be converted to unity, and what I will be left with is height or width. So this is my second pi term that I just derived by repeating the same step 5 for my pi 2 term. So now we have to do this for our next pi term, because in this case we have 3 pi terms. So in that case we will take our next non-repeating variables. In this case the only non-repeating variable that is left is our viscosity, and we will multiply them with the non-repeating variables and form our pi 3 term, and then arrange it like this. So let's repeat this step for our pi 2. So step 6 again is to repeat step 5 for our remaining non-repeating variable. So the one non-repeating variable is our viscosity. As you can see from this case, this is the only non-repeating variable left. The drag force is used, and pi 1 term is determined by using the drag force. Then we use the height, and also pi 2 term is determined by using the non-repeating variable height. So the only non-repeating variable that we are left with is the viscosity. So we will take viscosity and multiply them with our repeating variables. So let's do that. The remaining non-repeating variable is viscosity, so that our pi 3 becomes, and that is viscosity multiplied by the repeating variables, each raised to the power a, b, c, and we will now correctly assume the values of a, b, c to correctly arrange this pi term. So let's do that. Now first we will add the dimensions of each of these variables. So the dimensions of viscosity, the dimensions of width, velocity, and density will be equated to these 3 reference dimensions, each raised to the power of 0. So now we will write these equations to correctly write the values of my powers a, b, c. So this is 1 plus c for mass m. So mass m is here in the viscosity. So here the mass power is 1, then it is repeated in the density, and here its power is c. So 1 plus c is equal to 0. Then we will do the same for length, and for length here the power is minus 1, here it is a, here it is again b, and here it is minus 3c. So minus 1 plus a plus b minus 3c is equal to 0. So this is for length. Then we will do take the powers of time on the both sides and equate them. So time is minus 1 minus b, and this is minus 1 minus b is equal to 0. So these are my 3 equations, and with the help of these 3 equations I will now correctly write the values of a, b, c, and then I will put them in my pi term, and I will rearrange my pi term in its correct dimensionless form. So these are my values of a, b, c. A is minus 1, b is minus 1, and c is minus 1. Again, these are equated from these 3 equations. So now let's write these powers here. W will be minus 1 velocity will be raised to the power minus 1 and c will be raised to the power minus 1. So now my pi 3 term will be viscosity divided by width, velocity and density. So this is my third pi term, and now I have all my 3 pi terms that I needed to find. And now in the next step I will again check them for dimensionless, that either they are all dimensionless or not. And as you remember, we started our example with 3 basic dimensions, and these were my 3 basic dimensions MLT. So first I will check my 3 pi terms, pi 1, pi 2 and pi 3, that actually they are dimensionless in this for this for these basic dimensions, that these are my mass, length, time basic dimensions. And then again I will check my pi 1, pi 2, pi 3, that they are dimensionless for FLT also. I will convert my mass to force and I will write their dimensions pi 1, pi 2, pi 3, and see that they are also dimensionless for this for these 3 basic dimensions. So now let's move on to step 7. So now in step 7, what we are going to do, we are going to cross check all our pi terms and see that if they are dimensionless or not. And to do that, we need to convert all the dimensions of the variables in FLT form. FLT. Remember that we started this example and we wrote out the dimensions of the variables involved in mass, length, time dimensions. And what we are going to do, we are going to switch mass and write force in terms of mass, and we are going to then check that either our variables are also dimensionless in terms of FLT form. Sorry, not the variables but the pi terms that we just derived, that they are also dimensionless when we write their dimensions in the basic dimension FLT. So this is what we did right here. As you can see that these are our pi terms, and now we have wrote all the dimensions of our variable in force, length and time form, and you can see that now they are also dimensionless. So this is how cross-checking is done in dimensional analysis, that initially we will take one system of basic dimensions, we will make pi terms for them, we will make sure these pi terms are dimensionless in this system. Then we will also write these pi terms in terms of our FLT dimension, basic dimensions, and see that they are also dimensionless in this. They will be in this case f to the power 0, l to the power 0, t to the power 0. In this case they should be like this. So this is what we did, and this is what step 7 is all about, that we have to cross check our result. Now in the next step we are going to represent our results of the dimensional analysis, and we are going to write the pi terms like this. Here you can see that this is our pi 1. We can express the results of the dimensional analysis in the form this, that this is our pi 1 is equal to a constant, and this is pi 2 and pi 3. So pi 1 include the drag force term, that's why it's on the left hand side, and that is equated to the pi 2 and pi 3. Remember that this should also be according to the principle of dimensional homogeneity, and this right hand side, which is dimensionless, must also be equal to the left hand side, which is also dimensionless. So you can see that the principle of dimensional homogeneity in dimensional analysis applies from the start to the end. So this is what how we are going to represent these two terms, the height over width term and this ratio. These two ratios can be inverted and also written like this. And the height over width now becomes the width over height, and this term right here becomes the rho VW over mu instead of this. So we can also write them in this form because they are dimensionless, and they will still remain dimensionless when we write them like this. But these two ratios, this width over height, they have special names, and this is called the aspect ratio. Aspect ratio. And this was the aspect ratio of the plate that we saw in the example initially, the width to height ratio of the plate. So this is the geometry term. This is related to the geometry of our object involved. And this right here, then this next term, this right here, this rho v w over mu, this is called the Reynolds number. Reynolds number, and this is related to our flow. This is related to our flow of fluid. As you can see, the density, velocity, then the length dimension, and the viscosity. This is related to the flow, and the Reynolds number is used to classify the flow as turbulent or laminar. Basically, as you can see that Reynolds number is a dimensionless number, and this dimensionless number actually tells us that whether our flow will be laminar or turbulent, and this is the ratio that's how we represent the Reynolds number. So Reynolds number and many other numbers like Mach number are also dimensionless, and these dimensionless numbers are actually resulted from this sort of dimensional analysis, and that's why we represent them like this. And here, now let's write this final answer that we have in the form of an equation so that we can make a little bit sense out of this, that how are we going to represent the drag force from this equation, how are we going to calculate that. So we can write the drag force, that D is equal to, we will take this denominator and multiply that on the right hand side, that will be W square, the density, velocity square, and then the constant, and then multiply by the aspect ratio. Okay, so we have, this is the first term on which the drag force is dependent, and then plus the next term, that is this. So we will have, we will write this a little bit cleanly, so we can write this equation in a single line. So this was the drag force is equal to W square, density, velocity square, then the constant and the aspect ratio, plus this term again, width square, density, velocity square, constant, and our Reynolds number, that is rho VW over mu. So this is how we are going to compute our drag force from these different independent variables. And what we need to do, we need to find the value of this constant, and for that value of this constant we need to actually run some experiments first to actually identify the value of the constant, and then we can use this equation right here to see the effect of the drag force, that the effect of these different variable will have, these different independent variables. These are my width, the density, velocity, and the height of the plate, and other like this, dynamic viscosity, and this constant. What will be the effect of these variables when I change them? What will be their effect on the total drag force that was subjected on the plate? So this is how we are going to represent our final result, and that we got in this form. In this form right here, we can also represent it in the form of equation like this. And now you can see that how we are going to compute our drag force. We are going to write different values for our variables that are involved in this experiment, and we can actually compute our drag force. So now you can see that how with the help of our dimensional analysis, instead of doing many experiments, we can now actually do few experiments, and with the help of those few experiments we will actually like to compute the value of our constant. This is our constant, and with the help of then this equation, instead of doing experiment, we can then use this equation and see the effect of the different variables involved. That was the width of the plate, the height of the plate, the density of the fluid, the velocity of the fluid, the viscosity. These 5 variables, these 5 independent variables, we can see the effect of these 5 variables on the drag force to which the plate was subjected. So this was all done with the help of dimensional analysis, and this is what we said in the start, that dimensional analysis is done to reduce the number of experiments. So instead of doing experiments by taking different sizes of plates and by changing the type of fluids and by changing their viscosities, their densities, and then seeing the effect of the drag force, that would be a lot of that will cost us a lot of money and time. So this is what the dimensional analysis did. It simplified our experiment, and then instead of doing many experiments, we need to do few experiments to just compute the constant and then use the equation at the end to compute our drag force. So this is the comment at the end of the example, and to proceed it would be necessary to perform a set of experiments to determine the nature of the function, this function, as discussed in section 7.7 of your Munson book. So we now just need to do few experiments to actually predict the value of the function, the constant that is here in this equation. And by doing some experiments, and once we have this value, then we can use the equation that we just wrote and actually compute our value of the drag force. So this was example from your Munson book related to dimensional analysis. Hope this was clear.